Welcome to Programming Fluency. This is section 1.1. Welcome to C. In this short video, we ask a simple question. Why does a programming language from 1972 still matter today? Let's find out. Welcome, we start with one question. Why is C still so important after 50 years? The answer is one word, control. Let's see what that means. Here is the plan for this video. First, we ask why C has lasted so long. The answer is control over the hardware. Even today, operating system kernels, databases, and embedded systems are all written in C. Next, we look at what C actually is. It is a general-purpose programming language that Dennis Ritchie created in 1972 at Bell Labs. Then we compare source code and machine code. Source code is the text you write. Machine code is the binary the CPU runs. You will see how the compiler bridges the two. Finally, we walk through the compilation pipeline. You will see how a .c file turns into an executable, and how a compiled language differs from an interpreted one. Every operating system, every database, and every small device speaks C. This word C is everywhere. C first appeared in 1972. So why has C outlasted thousands of newer languages? The answer is one word, control. C lets you talk directly to the hardware. It does not hide how memory works, and it does not hide how the CPU runs instructions. So what is C? C is a general-purpose programming language. Dennis Ritchie created it in 1972 at Bell Labs. He built it to rewrite the Unix operating system. Unix was first written in assembly, a slow and machine-specific notation. Let's write down a simple definition. C is a general-purpose language that gives you low-level access to memory and hardware, while staying portable across different CPUs. Let's look at a small C program. Do not worry about every symbol yet. Just notice two things. A person can read it, and it is only 6 lines long. This readable text is called source code. You will write and run this exact program yourself in section 1.3. A CPU does not understand C, it understands machine code. Machine code is long sequences of ones and zeros. Each one tells the CPU to do a tiny job, like add 2 numbers. Machine code is different for each kind of CPU. Code built for an Intel chip will not run on the ARM chip in your phone. Source code is the human-readable text you write in a .c file. It uses English-like words like if, while, and return. Machine code is the binary the CPU runs directly. Source code is for people. Machine code is for CPUs. Something must bridge that gap. The bridge is a program called a compiler. It reads your .c source file. It checks it for mistakes. Then it translates it into machine code your CPU can run. The result is a standalone executable file. You can run this file on its own without the compiler. This is what makes C a compiled language. You translate the whole program first, then you run it. This picture shows the 3 stages of compiling. On the left is the source file. This is the .c file you write by hand. In the middle, the compiler reads that file and checks it for errors. On the right is the executable. This is machine code ready to run. Once it is compiled, the executable runs on its own. You only need the compiler during translation, not while the program runs. Let's trace one real example. You type the program and save it as hello.c, then you run gcc hello.c -o hello. Stage 1 is the source. Hello.c is plain text, about 95 bytes. A person can read it. A CPU cannot run it. Stage 2 is compilation. GCC reads hello.c, checks the syntax, and turns each statement into machine instructions. Stage 3 is the machine code. The file hello is now a binary. You run it with ./hello, and the CPU runs those instructions. One quick platform note. On Mac OS and Linux, you run these commands in the terminal. On Windows, use the MSYS2UCRT64 terminal you set up in section 1.2. The commands are the same. The only difference, gcc-o hello makes a file called hello.exe, which you still run with ./hello. This diagram has a gap in the middle. The source file calculator.c is 2 kilobytes of text. The program calculator is 16 kilobytes of binary. Something turned one into the other. What program does the change? The compiler, such as GCC or Clang. Why can't the CPU run the .c file directly? Because it is just text characters, not machine instructions. Why is the binary bigger? It holds machine instructions, plus startup code and extra data the operating system needs. Not every language works like C. Let's compare C with Python. Look at the run command. In Python, you type python hello.py in C. You type gcc hello.c-o hello and then ./hello. Now what happens? Python reads and runs each line at the moment you run it. C translates all the code first, and then the binary runs. And the runtime need. Python needs the interpreter installed every time. A compiled C program runs on its own, with no compiler needed. You might ask, if Python is easier, why learn C? Because some jobs need direct control over the hardware and memory. Operating system kernels are written in C. The Linux kernel is about 30 million lines of C. Small devices use C2. A tiny microcontroller may have only 32 kilobytes of memory, far too little for Python, but plenty for a C program. Databases like SQLite and PostgreSQL are written in C, and MySQL in C and C++. Even Python's own interpreter is written in C. C is not the easiest language, but that is exactly why it shows you what happens below the surface. Let's clear up a common mistake. Some students think C is fast because it is compiled. But compiling is about how you build the program, not a promise of speed. You can write slow C code with a bad plan, and you can write fast Python code with a good plan. Compiling removes the cost of reading source code while the program runs, but real speed depends on what your code actually does. Now a second common mistake. A beginner types ./hello.c trying to run the source file directly, but .c files are text. The CPU cannot run text. You must compile first, then run the binary. Type gcc hello.c-o hello and then ./hello. Running the .c file directly gives an error because the system expects binary instructions, not text. Let's recap. C is a compiled language. You write human-readable source code. A compiler turns it into machine code. Then the CPU runs the binary. First point. C is still essential when you need direct control over memory and hardware. Second point. Source code which people read becomes machine code, which the CPU runs through a compiler. Third point. Compiled languages finish all the translation before the program runs. Interpreted languages do it while the program runs. Next, you will install a C compiler and the other tools you need to start writing programs.